Hello, my name is Walter Swan. I'm a Regional Technical Manager with Tartar Steel, and today I'm going to talk to you about steel grades and specifications. In this presentation, I'll start by considering two aspects of the steel supply chain that can have an impact on how we approach the design of steel members. The first of these is the age-old conundrum of steel grade, S275 or S355. Which should we design in and why? The second concerns the two manufacturing processes used for hollow sections and the impact this has on the design capacities of what superficially appear to be the same section. We'll then move on and take a brief look at the steel manufacturing standards that your project specification will refer to. What are they there for and what do they do for us as designers? And then finally we'll investigate an area of steel specification that is often neglected, that of steel subgrade selection. So, S355 or S275, which grade of steel should we use and why? Let's start by taking a look back at past custom and practice. Once upon a time, the norm for open sections was to design in S275 JR material. This decision was based primarily on availability and based on the knowledge that all stockholders kept a supply of sections in this grade. Many engineers were aware that S355JR was available at a very modest cost uplift, but mill supply only. This had implications in terms of lead-in, and so was often only specified where depth was a critical design factor, or where the scale of the project made weight and cost savings attractive. And I'll revisit open sections in the next slide. Turning our attention now to hollow sections, it's been the case for many years now that hollow sections are supplied in a single grade, S355J2H. That's in both the hot finished and cold formed product, and this practice is now very well established. Back to open sections. There's been a significant change in the supply chain that brings some clarity to the S355 or S275 dilemma. The Tartar T-side beam mill has switched to 355GR as the standard feedstock. This means that the standard grade for all serial sizes greater than, but also including a 203 UKC, and all serial sizes greater than, but also including a 356127 UKB, is S355JR. This change in supply is outlined in the BCSA All Members Memorandum 20210. So designers should be aware that if they have specified S275GR, they may be getting something different, and if they really do want this grade, it would need to be ordered directly from the mill. Designers should also be aware that whilst in strength terms S355GR is clearly better than S275GR, this does not hold true in terms of toughness and brittle fracture, and we'll see why later in this presentation. In the UK, structural hollow sections are manufactured using two processes: hot finished, shown on your left, and cold formed, shown on your right. In both processes, a flat strip of steel, which has been stored as a coil, passes through a set of forming rolls and is first formed into a circular tube. The two edges of the tube are brought together and used in a high-frequency induction welding process, are heated and then fused together by a squeezing roll to form a continuous seam weld along the length of the product. No additional material is used in this process, and any excess on the outside is trimmed as a matter of course. This is where the hot and cold processes differ, with the cold going directly through the shaping rolls to give the product its final shape of circular, square or rectangular. In the hot process, the tube passes through a furnace to be normalized, and once at the correct temperature, it passes through the shaping rolls to be formed into a circular, square, rectangular or elliptical hollow section. Let's see how these two subtly different manufacturing processes impact on the properties of the final product. In the case of the hot finish section, the final shaping is done at normalizing temperature. The steel has a consistency like that of a stick of toffee left out in the sun, which allows improved metal flow during final shaping and a tight corner profile in the case of rectangular and square hollow sections. In the case of the cold form product, this final shaping process is done at ambient temperature. The steel is taken up to and beyond yield, and in the corners there is a risk of cracking. To reduce this risk of cracking, larger corner radii are used relative to the hot finished process. If we now put two sections of exactly the same serial size and wall thickness side by side, one manufactured using the hot finish process, the other the cold form process, we begin to see some physical changes. Physical changes due to the difference in the corner radii, and this can be very, very pronounced for thicker walled sections. Here we have a 120 by 120 by 8 rectangular hollow section, but one is hot finished while the other is cold formed. That larger corner radii in the cold formed section results in a reduced cross-sectional area, a reduced moment of inertia, and a reduced elastic modulus. In simple terms, it's not the same section. Let's now take a look under the microscope. Are there any differences here? And of course the answer is yes. The hot finished hollow section has uniform grain structure and uniform mechanical properties wherever you go. Why? Because the final shaping was done at normalizing temperature. The cold form section has varying grain structure and varying mechanical properties. The exact properties depend on how much yielding of the steel has taken place, how far up the stress-strain curve the steel was taken during manufacture. Clearly these effects will be more pronounced in the corners. This then begs the question, what happens when we apply heat to the section? Heat due to fabrication processes, and I'll pick up on that shortly. Let's consider the capacity of these sections under axial load. We appreciate from the previous slide that our cold form section has some locked-in stresses due to the manufacturing process, whilst the hot finished one does not. The code recognises this and suggests that designers should use a different strut curve, shown in blue on the slide. This results in lower axial capacities for the cold formed product. If we couple together the most unfavourable slenderness ratio with the greatest differential in cross-sectional area, a cold formed section can suffer from a rather significant 34% reduction in capacity relative to the hot finished product of the same serial size and thickness. Delving a little deeper, this slide shows some capacities for different sections. At the top of the table is a 406.4 by 8 CHS with a capacity of 4,606 kilonewtons for the hot finished product and 3,684 kilonewtons for the cold form product, a 20% reduction. Geometrically, circular hollow sections are exactly the same, so this difference is purely down to the different strut curves used in design. Taking a look now at the 120 by 120 by 5, we see a 21% reduction in capacity. So as well as the effect of the strut buckling curve, we're now seeing the effect of the larger corner radii having an influence, albeit a small one in this case. But then as we increase in wall thickness to 10 millimeters, the effect becomes more pronounced with a 24% reduction in capacity overall. If we now turn our attention to fabrication and consider the case of a tubular truss with internal bracings of the same size as the cord. The large corner radii on the cold formed product means that the fabricator is putting down more weld metal, possibly looking at multiple runs, or he could profile cut the bracings. Either way, it's additional fabrication and additional cost. But the fabricator and designer must also consider possible risks associated with releasing locked-in stresses local to the corners. And whilst there's no guidance in BS 5950 on this, there is in Eurocode 3. And this can prohibit welding in these areas. With the hot product, all these issues disappear. This is the guidance from Eurocode 3, and I don't intend to go through it in detail. Suffice to say, If the section doesn't comply with these rules, then the code suggests that there should be no welding within 5T of the corner. The zinc in a galvanizing bath is at a temperature of around 450 degrees C. With hot finished hollow sections, the risk of distortion due to release of locked-in stresses is very low, because the sections have been formed at normalizing temperature, and so any residual stresses from the processes are negligible. The cold formed product is manufactured at ambient temperature. There are significant residual stresses, and so there is greater risk of distortion. Having said that, galvanizing is not usually an issue with cold formed hollow sections, but issues can arise with certain types of fabrication detail. For instance, if you have a small, cold-formed internal brace welded to a hot-rolled open section cord, then it's possible to get distortion or splitting of the cold product. Also, for aesthetics, if you join two cold-formed members together with a weld, then this will have a different appearance than the rest of the tube once galvanized due to the stress relieving of the product when heat is applied. Moving on to certification. Hot finished hollow sections are manufactured in accordance with BS-EN 10210. This standard requires sections to carry a 3.1 specific inspection certificate, and it's a requirement for sections used in structural applications, i.e. buildings. Cold formed sections are manufactured in accordance with BS-EN 10219. Structural sections manufactured in accordance with this standard must also carry a 3.1 specific inspection certificate, but there's a but. And this is the but. BS-EN 10219 also provides guidance on the manufacture of cold formed hollow sections that are intended for other uses, non-structural uses. The level of testing required for non-structural applications is less onerous because the risk to public safety is far, far less. The issue for the building designer is put them side by side and you can't tell one from the other. The only way to find out if you have a structural product intended to be used in a building is to check the paperwork. I should perhaps point out the difference in the levels of certification. A 3.1 specific inspection certificate provides test data and analysis on the steel that is specific to the batch of steel used for a specific project. A 2.2 non-specific test report provides data and analysis for the manufacturing process and may not provide specific data relating to a specific batch of steel for a specific project. In concrete terms, it's like specifying a C35 concrete mix but not having test cubes to validate the design. So we've seen that the different manufacturing processes for hollow sections produce two different types of product in terms of their capacities and the way we treat them during fabrication. It follows then that an engineer cannot simply allow a hot finished hollow section to be replaced with a cold formed one without first checking the design. Likewise, the fabricator should consult with the engineer before a change is made, and the stockist must consult with the fabricator. Moving on now to consider how we specify steel, and starting with the steel standards. The language used here may feel a little bit alien. A long product to an engineer is a UKB or a UKC, and a flat product is plate. In building design, on the whole, we're dealing with non-alloy structural steels. Most project specifications will refer to three steel standards. They are BS-EN 10025 for open sections and plate, and that comes in 6 parts. There's BS-EN 10210 for hot finished hollow sections, and BS-EN 10219 for cold formed hollow sections. Although they may be of no direct use to us in design, it's useful to have an overview of what the standards do for us as designers. So, the steel standards, what are they? They're standards aimed at steel makers that provide guidance on the chemistry of the steel to ensure that desirable characteristics are delivered to the end user. What are those characteristics? Well, the There's the obvious, such as the minimum yield strength, and then there's some things that we possibly take for granted, such as weldability. Too much carbon or high quantities of other elements can present issues with welding, and this is controlled through something called the carbon equivalent value, for which a threshold value is given in the standards. The standards also ensure a very important characteristic of steel, that of ductility. As engineers, we like ductility. If a steel frame building gets into trouble, it will usually bend and stretch and send out a warning rather than collapse suddenly. The standards also ensure that structural steels are manufactured with an appropriate level of toughness, and I'll come back to that later on in the presentation. And finally, they also present guidance on appropriate levels of testing to ensure compliance with the specification. The steel standards also present a way of specifying steel. It'll be familiar to you, but you may not know where it comes from, and it comes from these documents. So we have an S to denote a structural steel, a number 275 or 355, which denotes its minimum yield strength. This is then followed by JR, J0, J2 or K2 to tell us what the toughness characteristics of the steel are. And this can then be followed with an H if we have a hollow section, or a W if we have a weathering steel. At the bottom of the slide we have three specifications. One for open sections in black, one for hot finished hollow sections in red, and one for cold formed hollow sections in blue. A word of warning here. There is sometimes a tendency to abbreviate the specification and omit the standard. On open sections you can get away with this, but if we abbreviate the specification of our hollow section to S355J2H, we're failing to give a critical piece of information that can have significant design consequences. That is, we haven't informed the fabricator whether the hollow section is hot finished or cold formed. If you cast your mind back, there can be a very significant difference in the capacity of these two products. An alternative, of course, is to specify product. For instance, Tata Steel's hot finished hollow section is Celsius and the cold formed product is Highbox. So moving on to what our design codes say and turning our attention to more familiar territory. If we open the pages of BS 5950 Part 2 and BS 5400 Part 6, we'll find these clauses. Both design standards require that steels used for buildings or bridges must have something known as specific inspection and testing. BS EN 10204 gives us a definition of specific inspection. And although both standards are now officially withdrawn, the requirements still apply. If I can draw an analogy with common practice for concrete, on most projects the specification will call for concrete cubes to be taken, and those cubes will be tested to give an indication of the strength of the concrete used on that particular project. In simple terms, specific inspection and testing of steel does exactly the same thing. It gives an indication of the characteristics of the steel used on a specific project. With 3-1 certification, the manufacturer is giving you a guarantee that the steel is correct. With a 2.2 test report, the manufacturer is saying the steel is similar to the report. Most engineers see test results for concrete cubes, but not all have seen an inspection certificate for steel. Well, now you can say you have. The inspection certificate here tells us that the product has been tested, it tells us the chemistry of the steel, and it gives us an indication of the strength characteristics of the steel. How do we know that this steel has specific inspection and testing as required by our design standards? Because here it tells us that this certificate is a 3-1 inspection certificate. A 3-1 inspection certificate, by definition from BS EN 10204, means specific inspection and testing as required by the structural design codes. Just for comparison, this is a 2.2 test report, and it looks remarkably similar to the 3-1 inspection certificate. but if you look closely you'll see that there are some significant gaps in the information that the manufacturer has to provide. The 3.1 inspection certificate is all about traceability of product. The 2.2 test report is about validating a manufacturing process. In the final part of this presentation, we're going to take a look at steel subgrade selection. But let's just remind ourselves of what we're looking for in terms of specification and what we need to do to get it right. As engineers, we think in terms of stress grade, S355. It's understandable because this is our baseline currency that we can use to compute member capacities. If we're on the ball and we prefix this with the relevant standard, then we've got ductility and weldability covered, as well as testing requirements. But what happens if we miss this last bit, the steel subgrade? What are the implications of not properly specifying the steel quality? Well, not surprisingly, cost creeps in. This is an extract from the latest Tata Steel price list, and it gives us an indication of the cost uplift for the different subgrades. So, specify S355GR when you actually need S355J2, and you have to go cap in hand to the client and ask for another £55 per tonne. Conversely, specify S355J2 when you only need S355GR, and you're costing the client money unnecessarily. Now, the cost differentials we're talking about are really quite modest in the context of the total building cost. And perhaps what's more of an issue is availability. At the start of the presentation, I mentioned that S355GR is now the standard grade for structural steel. So this is the main grade rolled at the mill. And perhaps more importantly, the only grade kept in stock by stockholders in any significant quantity. That means if the project requires anything other than S355GR, it will need to be ordered direct from the mill, and the mill rollings are every 4 to 6 weeks, and this would need to be accommodated in the construction programme. Some of you might remember this from your university days. This is one of the Liberty ships. They were British by design, but the Americans liked the design because they were cheap and easy to build. So several thousand were built in the US during the Second World War. You can see from the photograph that there was a bit of a hiccup. Several of the ships broke in two, like this one. But it didn't happen in heavy seas. Often it was in harbour, in calm conditions, and often it occurred overnight when temperatures dropped. It's also worth noting that there'd been a technological change in the shipbuilding industry at the time, and riveting was starting to be replaced by welding. And initially, the finger was pointed at this for the failure. However, a lady called Constance Tipper at Cambridge University did some research and discovered that the cracks occurred not because of the welding, but because of the grade of steel. When the temperature of the steel drops below a critical point, the mechanism of failure changes from ductile to brittle. In simple terms, this was a brittle fracture issue due to the incorrect specification of the steel subgrade. In riveted ships, the same issue may well have existed, but any cracks would stop at the next rivet, and so defects could be detected and remedied. Clause 2.4.4 of BS 5950 gives us a means of addressing any brittle fracture issues with building structures. It's relatively simple in its approach, but as you'll see, it deals with a relatively complex issue. The clause tells us that we need to take account of the minimum service temperature, thickness, steel grade, type of detail, stress level and strain level. So let's just expand on each of these a little. Most engineers understand that at colder operating temperatures, steel will behave in a more brittle fashion, and so a tougher steel must be specified. The classic analogy is that of a Mars bar. If it's left on a windowsill in the sunshine and then you try and snap it, it deforms and stretches and exhibits ductile behaviour. Put that Mars bar in the fridge for a couple of hours, bring it out, hit it with a hammer, and it will shatter into 1,000,000 pieces and exhibit brittle behaviour. The thickness is all to do with the rate of cooling of the steel. and how that impacts on grain structure. A thin flange section coming off the mill will cool quickly and uniformly, and so the grains will be small and of a consistent size. A thick flange section will experience differential cooling. The periphery will have small grains, but the internal body of the steel will have a larger, coarser grain structure. In steel making, small grains means stronger, tougher steels, and larger grains means weaker steels with lower impact resistance or toughness. To go from 275 to 355, steelmakers will often throw more carbon into the mix. This has the desired benefit of increasing the strength, but unfortunately it has a negative effect on toughness. And the way that the code deals with this is to reduce the limiting thickness for higher grade steels. The type of detail primarily relates to fabrication processes. For example, are holes to be punched or drilled? Punching will cold work the steel local to the hole and leave behind microscopic defects that can act as points of crack initiation. Drilling, on the other hand, is more forgiving. We need to take account of stress level. It's tensile stress that's of concern, be it from bending or direct application of load, as it will exploit any imperfections or flaws. Finally, the rate of application of the load or strain rate, not usually an issue for building structures which are effectively subject to static loading. So that innocuous small clause deals with a phenomena that is clearly very complex. But in the world of building structures, it's not often a critical aspect of design, and so we make life easy for ourselves. And this is how. We ensure that the thickness of the element being considered, be that the web or the flange, is less than the limiting thickness T1 taken from Table 4 in the case of open sections and plate, and Table 5 in the case of hollow sections. Tables 4 and Tables 5 allow for the steel grade and the temperature the steel will be subject to, and we multiply that T1 by a factor K that makes allowance for the stress level in the steel and the fabrication detail. Here is an extract from Table 4 that gives us the limiting thickness T1. This table allows for the effects of the minimum temperature that the steel will feel and also the strength grade and subgrade quality. You'll recall that to increase the strength of steel, carbon is usually added to the mix, but it has a detrimental effect on toughness. The way that BS 5950 tackles this is by reducing the limiting thickness for higher grade steels, and we see this in the table as we jump from S275 GR to S355 GR steel. We also know that as the temperature drops, brittle fracture becomes an issue, and again we see in the table that the limiting thickness allowed reduces as the temperature drops. Moving on now to Table 3. If we start in the right hand column and then move in, the multiplier K reduces as we move from compression to tension, because in issues of brittle fracture we're more concerned about tension. On the top line of the table, where we have plain steel, the K factors are highest, and as we do increasing amounts of fabrication, the multiplier drops. Now let's see how to apply that table with a bit of an example. So here we have a primary beam, thin plate to the left hand side, flexible end plate to the right hand side, and a bolted connection at mid-span from an incoming beam. We need to know a little bit about fabrication processes, and I'm going to make some conservative assessment about stress levels. Now most fabricators have a cut and drill line, so our beam will have saw cut ends and the holes will be drilled. Let's consider the left hand side. In terms of fabrication processes, as it's connected via a fin plate, it's simple drilled holes to the web of the beam. In terms of stress, we're at the end of the beam, but there may be some moment because we're inboard of the theoretical support. So let's conservatively assume that we have some modest tensile stress due to bending. That positions us here in the table with a K factor of 2 for the web. Now switch ends. On the right hand side, the only thing that's changed is that we're connecting via flexible end plate. And this is welded to the end of the beam. So we drop down the table with a K factor of 1.5, again for the web. Moving to the centre of the beam now, fabrication has drilled holes to the web, but we now have maximum tensile stress due to bending in the bottom half of the beam. So we move a column to the left and back up the table to drilled holes for a K factor of 1.5, again for the web. It's worth noting here that for the top half of the beam, where there's no tensile stress, the K factor would be 3. Let's turn our attention to the columns now. I'm making the assumption here that they are part of a multi-story frame, and although there may be some eccentricity moments due to connections, that the section remains in compression. So for both columns we'll be in the right hand side of the table. In the case of the left hand side column, we have a fin plate welded to the flange, which falls in the welded generally category, and so the K factor for the flange is 2. The only thing that changes for the right hand side column is the fabrication process, drilled holes. So we move up the table for a K factor of 3 for the flange. So that illustrates how it all works, and later in the presentation we'll use this to identify when we need to pay particular attention to steel subgrade selection. Meanwhile, let's take a look at a special case. This is a relatively common detail, a welded tubular truss. We're considering the node joint in the bottom chord at mid-span, so we have high tensile forces in the bottom chord. We need to identify the K factor for the webs and for the top flange. Back to table 3. We're in this column of the table because we have high tensile stress, but the webs have no fabrication and so are considered as plain steel. Therefore, the K factor is 2. Let's move on to the top flange. Same column in the table, and then in terms of fabrication, it wouldn't be unreasonable to assume welded generally with a K factor of 1. However, if we look closer, we see a category, welded connections to unstiffened flanges, see 6.7.5 and tubular nodal joints. And it's the tubular nodal joints that was added to the 2010 amendment of the code that advises us that a K factor of 0.5 is more appropriate. Now let's take this just one step further and consider this. Not the best of details due to access for welding, but is this any different? And of course the answer is no. This detail would result in a K factor of 0.5 for the web of the UKC. I should also add that if the UKC were rotated through 90 degrees so that the connection was to the flange, then the K factor for the flange would be 0.5. So what's the big deal? Well, with the K factor that low, you can often find that a higher subgrade J0 or J2 is required. These next few slides try to get a handle on this issue and identify when we need to focus our attention on subgrade selection. We're going to make some simplifying assumptions, so it's a relatively crude assessment. Let's consider internal steelwork first. If you cast your mind back to our simply supported beam, we had a minimum K factor of 1.5. So we'll take K equals 1 for UKBs acting as beams. We'll assume our UKCs are columns taking compression and use a K factor of 2. Armed with this, we'll look at all the sections in the Blue Book. We'll assume the fabrication will be to the thickest element, the flange, and we'll identify which sections have a flange thickness greater than KT1. And this slide shows the results. In S275 GR material, there are only 6 UKBs out of a range of 96 and 1 UKC out of a range of 36 that would need attention. When it comes to S355 GR, there are 21 sections out of a range of 132 that would need some attention. So for internal steelwork, it's not a major issue. and the standard subgrade of GR will cover the vast majority of steelwork. But what happens if we find that we need one of those 21 sections in S355 GR that need a bit of attention? Well, we have two options. Firstly, we investigate the detail. Is the fabrication to the web rather than the flange? And does that solve the problem? If not, we may decide we need a higher subgrade, say J0. But I'd suggest that rather than specify J0 for all steelwork, which would add cost and potentially have an impact on program, just limit the higher subgrade requirement to the sections that need it. For external steelwork, things are a little less clear-cut. If it's a major structure that you're designing, then a higher subgrade will be required because you'll be dealing with bigger sections. But if it's modest canopy walkways or cantilever brackets, then the standard GR subgrade will probably do. Now the treatment of hollow sections. Hollow sections are relatively straightforward because of the simple supply situation from Tata Steel in the UK. There's only one structural grade, and that is S355J2H, and that's for both the hot finish Celsius product and the cold formed high box product. If we assume external exposure, then from table 5 the T1 value is 55 millimeters. Now let's assume the hollow section is going to form the bottom chord of a tubular truss so that the K factor is 0.5. Therefore KT1 is 27.5 millimeters. The mainstream sizes of hollow section available in the UK have a maximum wall thickness of 20 millimeters. So for Tata Steel hollow sections, the standard subgrade covers virtually all possibilities. Jumbo sections, however, would need a little bit of thought. So, swapping standards now and moving to Eurocode 3. At this point, it's useful to remind ourselves of the title of BS 5950, Structural Use of Steelwork in Building. So the guidance given is in regard to brittle fracture in a building's context. And because, as we've seen, it's not something that leads the design, the guidance is simplified. If we turn our attention to BS EN 1993, Eurocode 3, its title is Design of Steel Structures. So it's broader in scope and encompasses other things besides building. So necessarily it becomes more complex. Our paragraph in BS 5950 has gone to an 11-page document and a 4-page national annex to the code. The approach is different too. You start with a temperature, and that temperature is lowered or increased dependent on stress level, steel grade, etc. Once you have the final temperature, the allowable thickness of material can be determined. In the UK, we have a piece of complementary guidance that makes life easier in the form of PD 6695. In it, you'll find two tables, one for internal steelwork and the other for external steelwork, with the temperatures that are familiar from BS 5950. This is a part extract of Table 2 for internal steelwork, and its use is easier to demonstrate how it works through an example. So here we are back to our simply supported beam again. At the ends of the beam where the fabrication is, we'll have a very low tensile stress, so I'm suggesting a ratio of applied stress to yield stress of less than 0.15. And again we have two connection conditions. A fin plate to the left hand side where the beam web is simply drilled to receive the bolts, and on the right hand side the web is welded to a flexible end plate. So back to Table 2 and considering the left hand side connection first. We have a bolted connection with a stress level below 0.15, and so for S275 GR material the maximum thickness of material permitted is 85 millimeters, and for S355 GR material it's 55 millimeters. Over to the right hand side connection. We have a plate welded to the end of the beam, and here I've chosen a welded moderate condition with a stress level less than 0.15. And so we have a maximum thickness of 60 millimeters for S275 GR material and 37.5 millimeters for S355 GR. So it's a relatively simple, painless process, but we might need some help on what constitutes welded moderate, or welded severe, or welded very severe. And I'm pleased to tell you that there's some guidance and preparation from the SCI that puts pictures of typical fabrication details against each of those descriptions to help us along the way. To summarise then, the Tartar mills on Teesside have switched to S355 GR as the standard feedstock, and so open sections will generally only be available in this grade. Structural hollow section is only available in S355 J2H, whether hot finished or cold formed. If you're asked to replace a hot finished hollow section with a cold formed hollow section, check the design, because in the worst case there could be a reduction in capacity of over 30%. If you are specifying cold formed hollow section, the only way to check that you're getting what you asked for is by looking at the inspection certificates. And for all structural steel, you need to ensure that you have a 3.1 specific inspection certificate. If it's anything else, you're not getting a structural product. And finally, the subgrade. GR will cover an awful lot, but give subgrade selection some thought if you have external steelwork, if you have heavy sections in S355 material, if you have weld-intensive details in an area of high tensile stress, or if you have sections with thick flanges or fabricated from thick plates. Ladies and gentlemen, that brings us to the close of the presentation, and thank you very much for listening.